All right, welcome. Dr. P here, and in this lecture we're going to take a look at electrocyclic reactions. Now, electrocyclic reactions are intramolecular reactions. So, cycloadditions were intermolecular pericyclic reactions. Electrocyclic reactions are intramolecular, just one molecule. We get a ring formed, and we have different stereochemistry depending on the conditions. All right, well, what's an example of that? Well, let's take the following example. And if I take this diene and I heat it up, well, like before, I get a cyclic concerted mechanism there. And I get a four-membered ring now with a double bond there. And I get the trans product plus the enantiomer. Now, if I do light, H nu, I get the same ring, only I get different stereochemistry. I get the cis stereochemistry. And these are reversible. I should mention that actually the Diels-Alder reaction is reversible. You can do what is called a retro Diels-Alder, but typically it's not done that much. These reactions, however, whether they are ring closing or ring opening, tend to be reversible. So if I had this molecule and exposed it to heat, it could open up back to the original starting material. But if I took this product and, let's say, exposed it to light, I would end up getting the following. Similarly, if I took this guy here and exposed it to heat, I would get that same product. So the question now is, why do we get these products? And once again, we will use molecular orbital theory to explain why we get these products. So use MO theory to explain products. All right, so let's take a look at our diene. So here's our diene, and we will have 1, 2, 3, 4. And I'll go ahead and put in my orbital, or my p orbitals here. And notice how I'm drawing these. I've got my line here, which represents the carbon backbone, sticks out at the ends. So I've got 1, 2, 3, 4 carbons, but 5 and 6 there, because I've got 1, 2, 3, 4, 5, 6. I have 6 total carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. But we don't have p orbitals on the two end carbons, those two methyl groups, because they're sp3. All right. So this is actually like drawing the molecular orbitals for a diene like we did for the Diels-Alder reaction. Our lowest molecular orbital, everything is the same phase. That's pi 1. And then pi 2, we've got one node. So we'll have one phase change there. Pi 3, we'll have two nodes. And pi 4, we've got nodes everywhere. That should be it. There we go. And of course we've got, what, 2 4 pi electrons. So 1, 2, 3, 4 pi electrons. And this is our HOMO. And under thermal conditions, we'll use the orbitals in the HOMO, the highest occupied molecular orbitals. So that means I'm going to redraw this as follows. So basically I'm just going to be drawing this guy right here. I'm just, instead of looking at it top down, I'm going to kind of look at it from one end. And now I'm going to put in my orbitals. So I have my node here. So I've got one phase like that. My node is here. So it switches phase like so. Now, in order to get new overlap, what happens is I have to get rotation about these bonds here. So these pi bonds break, and the molecule, or this part of the molecule, rotates. Same thing here. This pi bond breaks, and this rotates. And so if this rotates, if we look down this way, it's going to rotate clockwise, and this one will also rotate clockwise. I'll do like that, because our product should get, we'll have that. We won't worry about these phases for right now, but I'm rotating, so this guy is now there. And this methyl group, which was sticking out like that, is now going to be pointing up, okay, because I'm rotating that way. So I'm going to have my CH3. And then here I'm going to have my p orbital. And because it rotated this way, this guy's going to swing down, so I'm going to have CH3 there. So I get a trans product. All right, notice that I've got my new bond, and it is from orbital overlap of the same phases. Okay, so we need orbital overlap of same phases. So that's going to explain why we get what we do. And since we're rotating clockwise here and also clockwise there, we call this one con-rotatory. Okay? Now that's different than if they rotated in opposite directions. I mean, one way you can think of it is con-rotatory. So these guys are both, they're right here. They're sticking out like that. Okay? So if one rotates this way, this guy over here has to rotate that way, and we end up trans to each other. If one rotated clockwise and the other counterclockwise, they'd be cis, but that would be disrotatory. Now, how do we get disrotatory? Well, let's take a look. We've looked at the example where we used heat, so this is our thermal conditions, and we look at the HOMO. So let's look at what might happen if we have light present. Okay, so let's go ahead and take a look then. Draw these out. 1, 2, 3, 4. 1, 2, 3. Can take a little while. You will have to do this on the quiz, but hopefully not too much of it. All right, color these guys in here. Got a node. Whoops. Oh, crap. Here, let me just redo this. So, let's try this again. Try to keep your orbitals straight. You can see I wasn't focusing there. All right, let's try this again. 1, 2, 3. Oh my gosh, Wayne. All right. Pi 2, pi 1, pi 3 star, pi 4 star. Okay, same phase. Now we have the opposite phase. We have 2 nodes here. So now I'll get my phase change. That's the same as that, and then my phase change. And then my last guy here, I've got nodes everywhere. Okay, so in the presence of UV light, so if we go ahead and we shine our UV light in here, we'll get one of our electrons promoted. So just like we did in the cycloadditions, so the 2 + 2 cycloaddition, we got an electron promoted to make a new, maybe I'll circle it in red here, HOMO star. All right, so in cycloadditions, we looked at the HOMO of the diene and the LUMO of the dienophile. Or if it was a 2 + 2 cycloaddition, the HOMO star of one alkene and the LUMO of the other. For electrocyclic reactions, we're only interested in the HOMO. So for thermal electrocyclic reactions, it's just going to be the regular HOMO here. For photochemical electrocyclic reactions, we're going to look at the HOMO star. So now, with our HOMO star, if I draw my diagram like I did before, okay, I've got, let's see, that guy's up there, then down there, and then my shaded one here is up. So now in order to get this rotation, I'm going to rotate around this bond clockwise, but I have to rotate around this one counterclockwise. And that will now give me my good orbital overlap. I still have these guys. And in this case, I'm going to have my CH3s are both, sorry about squeezing that in there, but my CH3s are both sticking up. And we call this type of rotation disrotatory. Okay. So we can use this to explain the, sorry about that, we can use this to explain the types of reactions that we get. All right, now so far we've just looked at 4 pi electrons. So here we have 4 pi electrons. We can do something similar with 6 pi electrons. And it would look something like this. And we'll go ahead, here's our new single bond there. That goes there and that goes there. And so now we have that and that. And in this case, when heat is present, we actually get the cis product. So it's the opposite. If we have UV light, that's when we get the trans product. And so we can, depending on which way things go, we could get this or it's an enantiomer. And then treating this with light will open the ring back up. But what we see is we don't go back to this product. Instead, what we get is the following. So this methyl group is trans here, but now this one is cis to the rest of the stuff there. So sort of like how we got a different opening in different conditions for the 4 pi electron system. The 6 pi electron system does something similar, but it's basically opposite. When we've got our methyl groups pointing out like this, trans to the rest of the molecule, when heat is present, we get the cis product. The 4 pi electron, when heat is present, we got the trans product. And we can explain this with a molecular orbital picture as well. And I'm going to let you guys give that a try. It should be in the text as well. Let me check real quick here. Let's see here. Murray chapter 30. So yeah, in section 30.2, he does describe this, and so you can look at those figures, and I'll go over some of this again in when we meet in person. And he doesn't do it quite the same way I do, but I think you can get a good feel for it. But I'll go ahead and I'll go over this type of diagram, but for 6 pi electrons. So a fun thing to do might be to actually try drawing this out for all 6 molecular orbitals. Figure out your HOMO and figure out why it gives you this product instead of this product. What we end up getting at the end is we'll get a set of rules, a set of Woodward-Hoffmann rules. And so we'll have our number of pi electrons. And if we have 4n pi electrons, where n is an integer, our thermal reaction will proceed con-rotatory, which is what we saw, and our photochemical reaction will be disrotatory. If we have 4n plus 2 pi electrons, it's the opposite. The thermal reaction is disrotatory, and the photochemical reaction is con-rotatory. So those are these rules are things that you should, I would say, understand, but I will provide you with the Woodward-Hoffmann rules on quiz and exam. So we can sort of summarize these. I apologize for my dog barking there. We've got our Woodward-Hoffmann rules for electrocyclic reactions. And then we saw, all right, Flint, we know you're here. We saw, Flint is the dog, of course, who is barking at the delivery person. Anyway, these other Woodward-Hoffmann rules from Lecture 2 are for cycloadditions. So these are the Woodward-Hoffmann rules for cycloadditions. And these new ones for this lecture are for electrocyclic reactions. All right. Well, go ahead and try drawing out the molecular orbitals for the 6 pi system and see if you can get a feel for that. And if you're still having trouble, that's fine, because we will talk about this in person in the next class meeting. All right. Well, until then, I will see you guys later. Stay safe out there. Bye now.